In the last several videos, we have looked at all of the different functions available in the data menu, and today we will look at the last one, which is process time domain electrochemical impedance spectroscopy data. This is quite a bit more specific than the more broadly useful features that we have looked at so far, and I want to start by emphasizing that we will not talk about any equivalent circuit fitting. This can be done in Relaxys. You can find more information about Relaxys on the RHD Instruments website, but Edelweiss does not contain any kind of modeling of impedance data, so we will not talk about it in this video. We also will not talk about the EIS applications that are built into Edelweiss, but we will just use them for plotting in this video. So what do I mean by time domain EIS data? Well, I have several spectra here of a lithium-ion battery, and I can plot a Nyquist plot of one of them. And each of these data points, of course, corresponds to the impedance of one frequency. And these impedances are calculated from the AC current and voltage applied to the cell. And some instruments also allow you to record this underlying data in addition to the impedance spectrum. So not only this frequency domain information, which is, for example, a Nyquist plot, but also the time domain data with potential and current versus time. This data is recorded by a Metron Autolab device, and here you can record this data. So in addition to the spectrum, I also have this table that contains the time, current, and potential. This table contains all of the frequencies, so you might be able to make out in the time domain data series that the values are increasing and then they keep resetting to 0 for every new frequency. So it's basically a step time that is recorded. And to show this data properly, it might be useful to have some information about how to group this data into each separate frequency. So to do that, I'm going to also select my other two tables containing the time domain data, and then right click on the time domain and choose create group data series and increment on reset, since the time resets every time we have a new frequency. And if this is unfamiliar to you, you can see more in the tutorial video about creating group data series. I choose yes and yes to do it for each table, and maybe I will also double click on this to rename it to something like frequency number, and choose yes to do it for all three tables again. So now I have this information about the frequency in each of these three tables. And if I plot the current versus potential and I split it based on this frequency number, I will also label it based on that. Now we see all of this time domain data. If I look at just a few of the traces, these are then Lissajous curves, as you might recognize. And each of them corresponds then to one impedance data point in the Nyquist plot. But this time domain data also contains some more information, and this is what we can get with this process time domain EIS data function. So to do this, I will open the table that contains the time domain data, and I will also select the other two tables in the data tree to repeat this data processing for all tables. So I don't have to select any data here, I can just go to data and process time domain EIS data. And now we get this dialog where at the top we can select our data, and as you can see it's already selected for us. So we have a few different data series that we have to select. We have to have a group data series in the case when we want to do the calculation separately for each different group. So in this case it's for each frequency. And then we have the time, potential, and current, all of which are correctly identified. And then here at the bottom we have several different options for what kind of calculation we want to do. And we'll go through each one in this video, and the first one is to calculate some quality indicators. So I choose OK and yes to do it for all the tables. We get one new table for each of the raw data tables. This contains the calculated quality indicators. It's too much for this video to go through exactly what these quality indicators mean, but you have the THD or total harmonic distortion, the NSD or non-stationary distortion, and then the NSR or noise to signal ratio. And if you want to know more, I can recommend going to the help pages, for example by selecting what's this and then process time domain EIS data. And here you can see there's a link to more information about EIS quality indicators. But let's plot all of these quality indicators for one of the tables. I will choose a logarithmic x scale for the frequency. And we can see that one trace is quite a bit higher. It goes up to about 16%. This is the noise to signal ratio for the potential. Whereas The other ones are quite low, below 2%. This indicates that this data, at least in the high frequency region, is quite noisy. It has a high noise to signal ratio. And maybe if I select all of the tables and plot just this NSR for the potential, yes, to do it from all tables. And I will rename this based on the table name instead. Table name. And again, choose a logarithmic frequency axis. Now we can see the high noise to signal ratio that we had before. This is for 1 milliamp amplitude, and for 10 milliamp and then 100 milliamp amplitude, the noise goes down significantly. So this is the kind of additional information about the quality of your spectra that you can analyze based on the time domain information. The highest amplitude here of 100 milliamps is high enough to induce some nonlinear effects, so I can use that to demonstrate how to calculate some higher order spectra. So I will go to the 100 milliamp time domain data and choose data, process time domain EIS data. And now we can choose calculate EIS including higher harmonics. And this is a galvanostatic measurement, so I will choose GEIS. We can choose which harmonics we want to calculate. This will calculate the fundamental frequency as well as the second order spectrum, but you can also calculate third, fourth, fifth, whatever by changing this number. So I'll choose yes, and now we get two more spectra for the first order and the second order. So first of all, we could compare this to the spectrum that was calculated by the instrument, and this is quite well overlapping, of course. It's not completely the same though, which is interesting, so probably the instrument does some kind of correction that slightly changes the impedance values. But what is interesting for us is perhaps to look at the second order spectrum, so I can choose those data series and again plot it as a Nyquist plot. And again, it's outside of the scope of this video to go through how to analyze higher harmonic impedance spectra, but quite typical here for these kind of lithium-ion batteries is that you get most of the data points close to zero, and then you get these kind of spirals. And the size and shape of this spiral can tell you something about the symmetry of the oxidation and reduction reactions of each electrode. Next up, we can also look at the raw Fourier transforms of the current and potential data series by selecting Calculate Fourier Transform Spectra. And here we get the Fourier transform of both the potential and current with frequency for each group. So perhaps we plot the potential Fourier transform, and I will split it based on the group. Maybe just label it from the group, and I will do it on a log-log scale. So choose logarithmic for both x and y. These are then the raw Fourier transforms. If we look at the first one, this is for 1 megahertz, and we can see the peak at 1 megahertz indeed. And otherwise it's mostly noise as expected, but we do also have some peaks at the multiples of 1 megahertz, so 2 megahertz, 3 megahertz. And that is of course what enables calculating the higher order spectrum. And then we can see the peaks shifting to lower frequencies as we measure the lower frequencies. There is one more option in the dialog that we've looked at, and that is calculate full impedance spectrum. Now for this data, this doesn't make much sense. This will just again calculate the impedance spectrum for this data. But to demonstrate this feature, I have some other data loaded. This is measured by a biologic SP200 potentiostat, and I can show you the potential and current versus time traces. So as you can see, this is kind of semi-random current steps and the corresponding potential. And based on this data, we can actually calculate the impedance of the battery cell. And this can be useful for quite low frequencies, since this takes a long time to measure with normal EIS. But when you do these kind of time domain measurements, you have a lot shorter measurement time. So let's just select this table and again go to process time domain EIS data. Here I will untick this group data, since I just want to calculate the whole data set without splitting it based on frequency or something like that. And the rest of the data series are correctly identified, and I will choose this calculate full impedance spectrum. And this we could now compare to an actual impedance spectrum that I measured for the same cell. First I want to change the units here, so I will select the real impedance and press Ctrl U and simplify unit, which will convert it to proper ohms. Do the same for the imaginary component as well as the magnitude. And also for the phase, this is in degrees, but if I choose simplify, I get radians, choose yes to recalculate, and radians is actually what we get from this calculation. So let's now plot the Nyquist plot again. So this is the actual impedance spectrum that I measured. And if I go to my calculated spectrum based on the time domain data, I can add it to the plot. And here we can see that it's overlapping very well with the actual spectrum. Of course, we cannot measure the high frequency part, but for the low frequency part, it overlaps very well, but it's a lot more noisy. And this has more to do with the fact that we get a lot more data points. So for a better comparison, we might want to smooth this. And I have actually created a little application as a workflow that we can import to smooth this data. So I'll choose import workflow. And I won't go in detail how this works, but it bins the data together to spread it out in frequency and get less noisy data. So if I add this, you might be able to see that we have a lot less noisy data, and this overlaps quite well with the actual impedance spectrum. Now it might be a little bit difficult to judge how good this overlap is, since we don't have any information about the frequency in this plot. So for completeness, let's just also plot the border plot. I'll select the frequency, magnitude, and phase, and then I can choose the border plot. And let's now add the calculated spectrum. So we see that also the frequency overlaps quite well, just that we have quite a bit of this noise. So if I add my smooth data, frequency, magnitude, phase, drag it to the plot, we can again see that the overlap is pretty good. And the impedance spectrum in this range took about 10 minutes to record, while the semi-random current steps were about 20 seconds. So it's a lot faster, and you can get more or less the same information. And if you want to know more about this technique and more in detail about how this smoothing was done, we will publish an application note on this topic, which will be available on the RHD Instruments website.